Hi there, AP Calc gang. Here's lesson 6 for exponential growth and decay. Even though this is in a calculus text, you'll recall a lot of this as pre-calculus-ish ideas. Really not a lot of calculus here, but we'll go over a couple examples. You'll be presenting a problem with one of your classmates, essentially, for this. Alright, so here is exponential change. Y equals y sub 0 times e to the kt. Just to identify what some of these things are. So the y, this is the ending amount, and oftentimes that's what we'll be looking for. This y sub 0, this is the initial or starting amount. E, remember, is a number, and it's associated with exponential growth a lot of times. This k value here is a constant, and many times we'll have to try to figure out what that k value is. T, of course, is some time factor, and the problem will dictate whether that's measured in minutes or years or whatever. Alright, now oftentimes we'll be trying to kind of get at these variables here, and you may or may not remember a lot of stuff about logarithms, but the way to really get at an exponent, in other words to solve for an exponent, is to take the logarithm of each side, and we'll get to that here in one of our examples, and we'll see that a few different times. Alright, here's our first example that we'll try to go through here. This is a colony of bacteria growing under ideal conditions, so the population increases exponentially. So at the end of 3 hours there are 10,000 bacteria. At the end of 5 hours there are 40,000. How many bacteria were present initially? Well, we're going to look at this first exponential equation again, which is this one that we just saw in the previous slide. We're given some info here. We know that there are 10,000 bacteria after 3 hours. So I'm going to write this as e to the k times 3. And there are 40,000 bacteria here after 5 hours. So those are a couple little equations I have there. Now if I divide those, or I'll just write it like this actually, so I have the 40,000 one like that equals y sub 0 e to the 5k, and if I were to divide that by the other equation, you might wonder why I would do this, but you'll see a nice thing will happen eventually here. That's e to the 3k. I can divide these, of course. 40,000 divided by 10,000 is 4, and the y zeros will cancel out, and I'll end up with e to the 2k power. When you divide exponents you can subtract them as long as they're exactly the same, so I get that particular expression. Now, as I was talking about, I'd like to solve this for k. So I'm going to take the ln, the natural log of each side here, and sounds like my time is up here, but no, you're stuck with me for a little while longer. So I'm going to do that, and the advantage of doing that, which you may or may not remember, is when you have the log of an exponent, this exponent can come around up front here. So basically this will turn into the ln of 4 equals 2k times the ln of e. And you also may or may not remember, but right here, anytime you see this ln of e, the ln of e equals 1. We can talk about why that's true as well. So, getting back to our little problem here, we have the ln of 4 equaling 2k. So that means k will be the ln of 4 divided by 2. That's going to be approximately equal to 0.693. So that's kind of an important variable here, as we'll see here in just a little bit. Keep that in mind. We're going to move to the next slide. All right. So getting back to what we have here though, we're going to try to figure out what that initial value was. So I am going to go back to one of my earlier equations, which was 10,000 equals y to the 0 e, and it was 3k, but remember our k value was about 0.693, like that. So that's going to be y sub 0 e, and 3 times 0.693, real quickly here, is 2.079. And how am I going to be able to solve this for y sub 0 now in this case? Well, once again, I'm going to take this natural logarithm of each side. So I'm going to have the ln of 10,000, and that's going to equal the ln of all this other stuff, y sub 0 times e to the 2.079, like that. Now when I have the log of this product here, I can essentially split this up as the ln of y to the 0 plus the ln of e to the 2.079. But again, here's a log of that power, so that means I can bring that 2.079 out in front, and as we saw earlier, that ln of e is just going to be 1. So I'm getting close to my final answer here now. I will get that the ln of y sub 0, and I'm going to basically subtract these two values here, so it'll be the ln of 10,000 minus this. And if I actually figure that out then, decimal wise, that's going to be 7.13 approximately. You can verify that. And how do I get then what my y sub 0 is? Well, one of the laws of logarithms says that the base here of this natural log is e, so e raised to this power will equal y sub 0. So if you take e to the 7.13 power, you're going to get about 1,250. That's my initial value of that bacteria colony. Kind of weird. We'll do more examples like that. Some of this logarithm stuff will come back to you a little bit easier. Alright, last example we're going to do, Newton's law of cooling. This is kind of a famous type of problem that you see in some calculus textbooks. Here's what that is, that the final temp that we're looking for is equal to the room temp plus the heated temp minus the room temp, and then all of that times e to the kt. So there's that nasty k value there once again. So here's my particular example. In a 72-degree room, a cup of 180-degree coffee will be 150 degrees after 2 minutes. How long will it take to reach 120 degrees? Well, I'll just kind of follow this formula here a little bit. So my final temp is 150 right now. The room temp is 72 plus the heated temp is 180 minus the room temp is this times this e to the kt. I can actually put a 2 in for t in this case because it tells us that. So simplifying this a little bit then, I can subtract 72 from each side, so I'm going to get 78. 180 minus 72 is 108 e to the 2k. I can actually divide by 108. That might simplify things a little bit. That's going to reduce down to something like 13/18, I believe. And that's going to be that e to the 2k. Once again, to get at that 2k, I'm going to take the natural log of each side. So ln of 13 over 18 equals, and I'm going to write it quickly like this, 2k times the ln of e. When you take the log of an exponent, that exponent can come out in front. Again, that's one of the key reasons we do this. The log of that exponent will be able to come out in front like that. And ln of e, of course, is 1. All I really need to do now is divide both sides by 2, and I will have solved for that k value. And sure enough, that k value is going to end up to be, let's see, about negative 0.163 or thereabouts. I could certainly get a little bit more accurate. Okay, now that will be sort of important because I'm trying to figure out how long it's going to take to get to 120. So I'm going to go to my next slide and figure that out. Okay, so this time, again, my room temp, final temp, remember in this case we want it to be 120. Room temp is still 72. When I did the heated temp minus the room temp, that was still going to be that 108. And then I have my E. Now this time I know what the K value is, negative 0.163 to the T power. And I know I want this to get 120. Puma, get out of here. Had a cat alert there. Okay, so I can subtract 72 from each side. I'll get 48 equals 108 times e to the negative 0.163t. Again, I'm going to divide 48 and 108, so that ends up to be 4/9 if you do that. Like this. Again, I'm going to take that ln of both sides once again. So it's going to be like the ln of this and the ln of this. And so the ln of 4/9 is going to be negative 0.163t times that ln of e. ln of e is going to be 1, of course. So I really just have to divide this by that negative 0.163. And my t value, you can verify this, t is going to end up to be around 5 minutes, which makes sense. So really that's just some pure algebra going on there. And again, we'll see some problems like this when you guys present them. Nothing terribly difficult as far as the mathematics goes, but just trying to keep everything straight, and the algebra gets a little complex. Alright, thanks for watching. We'll see you later.